Hi, in this video I will talk about red-black tree, simply called RBT tree. I will explain why we need red-black tree. I will first talk about sequential search. Then, to overcome the disadvantage of sequential search, I will talk about binary search. And then talk about binary search tree. To improve insert or delete the efficiency of insert and delete operation for BST tree, people invented AVL tree, which is called balanced binary search tree. And finally, I will explain why we need red-black tree, simply called RBT tree. First, we talk about search. Search is an important operation for finding information in data collection. For example, you may search file in your computer. You may search something on the internet, such as search red-black tree in the Google search engine. People often search something from the database. So search is an important operation in computer science and daily life. There are many search methods. Each search method depends on the underlying data structure. Sequential search is the simplest search method. Sequential search is also called a linear search. It searches a sequential sequence. It searches a sequential array by one comparison to find an element. For example, in this array, this is array of number. If I want to search number 4, I will compare 4 with every element in the sequence. First compare with the first element, then second, then the 3, 4, 5, 6. Then we find the 6th element is equal to the search element. If we search 5, the number 5, we also go from the first, second, 3, 4 to the end. We didn't find the number 5 in the array in the sequence, so the search is failed. The sequence search is very slow in time, because if the array has n number of elements, then we should compare n times with each element. So people invented another search method called binary search. Binary search is for ordered sequence. For example, this sequence is ordered from small to large. If I want to search in this ordered sequence, we can compare the search element with the middle element of the sequence, this element in the sequence. 4 is smaller than middle element 6, so we will search in the left half If the search element larger than the middle, then we will search on the right half. So the next search we are in the half of the orange sequence. So in this half sequence, we will compare the search element with the middle element 3. 4 is larger than 3, so we will search on the right half of the sequence, this half sequence. This sequence has just one element. When we compare the middle is this element. They are equal, so we find it. If we search the number 5, 5 is also smaller than the middle element, so we will search in the left half of the orange sequence. For this, when we search in this sequence, we still compare with the middle element. 5 is larger than middle element, so we will search in the right half sequence. This sequence has just one element, and 5 is not equal to this, so the search is failed. For binary search, if the orange sequence is the length of orange sequence is n, when we compare with the middle of the sequence, if they are not equal, then we will search in the left half or in the right half. So the next search will in the n divided 2 length sequence, and the length of searched sequence will always divided by 2. So the 3 search will in this length sequence. If n divided 2 power k less than 1, then the search is stopped, and we will failed or success. From this, we can find 2 power k larger than n and k larger than, so k is equal to log 2n. So this binary search is very fast. For example, if n equal to this, for sequential search, we will compare this number of, we will do this number of comparison. But for this, we just to compare equal to 10. We just do 10 comparison. Then we can find this element, at most 10 comparison. Or we failed to find the element. So the binary search is very fast compared to the sequential search. But this binary search must for ordered sequence. Binary search is very fast for ordered or sorted sequence, but insert or delete operation require a lot of time, require a lot of movement. For example, if we want to insert 5 to the sequence, 5 should be inserted here, and we must move from here to the last or to the next position. Then we insert a 5 in this place. So for the sequence, sorted sequence, the binary search is very fast, but the insert may require many movement, which is time consuming. For delete operation, also has the same problem. To overcome these disadvantages, people invented a binary search tree. Binary search tree is not a sequence, but a tree. For binary tree, the search is in efficiency as binary search on the sorted sequence. And we did not move many elements for insert and delete operations. For example, this is a binary search tree. For this tree, every node had at most 2 child nodes. One is called a left node and the other is called a right node. So it is a binary tree. Also, it is a binary search tree because for each node, the key of left tree is smaller than the key of this node. For each node, all the nodes in the left tree has keys smaller than the key of the node. And for the right subtree, all the nodes in the right subtree with keys larger than the key of the node. For each node has the same property. For example, for this node, all the nodes in the left tree has keys smaller than it. And for its right tree, all the nodes in the right tree has keys larger than the key of the node. This binary tree is called a binary search tree. For binary search tree, if we want to, because the tree is sorted. If we search number 4 in this tree, we compare with the root. 4 is smaller than 8, so we if there exists a node has the same key as 4, it must in the left tree. So we will go to left tree to search because 4 smaller than 8. We go left. In this tree, 4 is larger than the root of the tree. The root of the tree 3. So we will go to the right tree of this node. We will search in this tree. In this tree, 4 is smaller than the root of the tree 6. So we will go to its left tree. In this tree, 4 is equal the root of the tree. So we find the node. We just compare 4 times. Compare with this, compare with it, compare with it, with 4 times. If this is a sequence, we must compare 13 times. We see another example. If we search 5, it is smaller than 8, so we search in this tree. 5 is larger than 3, so we will search in this tree. It's right tree. 5 is smaller than 6, so we will search in the left tree of the 6. 5 is larger than 4, so we'll search in the right tree of the 4, but the right tree is empty, so we didn't find the number 5. So for binary search tree, if we search an element, we go from the root at most to the left, at most to the left. If we search 3, we just compare 2, then we find. If the element is not in the tree, we may go from the root to the leaf. So the time is the height of the tree. The tree has height 3, so at most 4 times to compare. First, we compare with the root, then with the children of the root, then children of the second layer. Then we search in the 3 layer and find the 4 layer. So the number of comparison is at most the height of the tree. So the time is O tree. And the height generally less than n. For example, there are 10 elements, but the height is 3. If n is very large, for example, n equal to this number, and h may be 10. So the search in binary tree is similar to the binary search in the sequence. It is very fast. Now we look at the insert operation. To insert an element, for example, we want to insert 5 to the tree. We first search the location to insert. We search 5 in the tree. 5 less 8, large 3, less 6, large 4. So 5 should be inserted here. So the search is first, the insert operation is first search the location to insert, then we insert. Insert the element to the right location. So the insert is as fast as search operation and did not move many elements. We did not move elements. So binary search is very fast for search operation and insert operation and delete operation. We see another example. If this is an empty tree, we insert 8, it will be the root of the binary tree. And we insert 10, insert 14, 3, insert 6, insert 1, insert 7, insert 13, insert 4. If the binary tree is balanced, that is, for any node, the height of the left tree is almost the same as the right tree. We call this tree is almost balanced. For the balanced binary tree, the height of the binary tree is equal to this number. This number is less than n when n n go to infinity. So for this kind of tree, the search, insert, and delete operation is very fast. But if the binary tree is not balanced, such as this is like a sequence. This is just a sequence. So the search time will be same as the search in the sequence. The search time is n for the last element or element not in the sequence. Generally, the search time is n divided 2. So if we want the search delete and insert operation to have good efficiency, the BS tree must be balanced. So people invented the AVL tree, which is a balanced tree. AVL tree is named after inventors, and we also call AVL tree balanced binary search tree. It has these properties for any node: the height of the left tree and the height of right tree, the difference at most 1. For example, the height of right tree, subtraction height of left tree is called a balance factor, which is smaller than 1. For example, this tree is a AVL tree, also balanced binary tree, because for each node, the balanced factor is 1. This is negative 1. Because the height of the right tree is 1, the height of the left tree is 2, so the balanced factor is negative 1. For this node, the height of the right is 1, 2, 3, 4 is 4. The height of the left tree is sight, so the balanced factor is 1. For each node, the balanced factor is at most 1. So this is a balanced binary search tree, also called AVL tree. And the height is this. So the time is very fast for search, insert, and delete. We will see how to insert an element in the AVL tree. If this empty tree, then insert element becomes the root. Then we insert 24. It will be the right child of the root. And the balance factor, this is 1, this is negative 1, this is 0. When we insert this number insert here, and the balanced factor is negative 2, so this tree is not balanced. For this case, we must adjust the tree to make it balanced again. How to adjust it? This is like this shape. We insert the element. This is called a minus unbalanced tree. We insert the inserted loader is the right child of the unbalanced ancestor loader. For this kind of unbalanced tree, this case for this unbalanced tree is called RR type unbalanced tree. For this unbalanced tree, we just rotated around this load, rotated this load to be the left child of this load. Then the tree will become balanced tree. Now we insert another number 90. The balance factor becomes this. Insert 53. The tree becomes this. From the inserted loader, we go upside to its ancestor load and find a load, the balanced factor, absolute value of the balanced factor is larger than 1. So this load is not balanced, and the tree root at this load is a minist unbalanced tree. This unbalanced tree is different from this. The inserted loader is a left child of the right child of the unbalanced loader. This kind of unbalanced tree is called RL type. For this type of unbalanced tree, we also need to adjust it to a balanced tree, but we need 2 rotations. First, we will rotate the low loader to between this load and this load. Then it become RR type. For the RR type unbalanced tree, we rotate around this load, make it to be the left child of this load, and this load becomes the child of this. So it also become a balanced tree, and this load is also balanced. There are 4 cases for the minist unbalanced tree. These 4 cases is AL type, R type, LR, and RL type. If the inserted load is in the left tree of the left child, left tree of the left child, the inserted load in the left child, left tree, in the left tree of the left child. For this LL type, we rotate this load to be the right child of this load, and this tree, the right tree of this load, will become the left tree of this load. The right tree becomes the left tree of this load. Using this right operation, the unbalanced tree becomes a balanced tree. For R type, if the inserted load is in the right tree of the right child, right tree, it is called RR type. We just do left rotation. This zero rotated to become the left child of this node, and its left tree becomes the right tree of the node, or the tree is become a balanced tree. For LR type, if the inserted tree is inserted on the left on the right subtree of the left child, right subtree. If we insert a load in this or in this, and make this load become unbalanced, this kind of unbalanced tree is LR type. For LR type, we also need two rotation. First, we rotate the load lower to between these two loads. And the left tree of this load becomes the right tree of this load. This is LL type, so we need another rotation. This load rotated to the right child of this load, and the tree is become a balanced tree. Another type of unbalanced is RL. Insert a load on the left child of the left tree of the right child, left tree. If we insert something in here or here, and make this load unbalanced, this is called RL type. First, we rotate the lower load to between them, become this. For this, we rotate the top to the left child and make the tree balance again. So for the AVL tree, if we insert a load and make the tree not balanced, we use the 4 type of adjustment to make them balance again. AVL tree is very good because the height of the left tree of any node is almost the same. But AVL tree need often adjustment. For insert or deletion operation, the tree always become unbalanced and always lead to adjustment. So people invented another tree called red black tree, simply called RBT tree. RBT tree is also a binary search tree, but in this tree, each node has a color. Each node has a color red or black. We should note The left load are different in BST and RBT tree. For BST tree, the left load, these two loads are left load because there is no child of this load. But for RBT tree, the left load is a lower point of the load. This load has no left child and right child, and the right child is low in the binary search. But in red-black tree, we also call the low empty tree, low load, left load. We call this low load left load, and this load become into load. So the left load concepts are different in BST and RBT tree. RBT tree also need rotation to make the tree balance, but RBT tree need less rotation during insert and deletion than AVL tree. RBT tree are less balanced compared to AVL tree. If insertion and deletion are often less frequent, and the search is more frequent, then we should use AVL tree. Otherwise, we should use red-black tree. RBT tree use color rules to keep tree balanced. What are color rules? For RBT tree, there are 4 properties related to the color. The first property is root property. That is to say, the root of the RBT tree is black. The color of the root should be black. Leaf property. The leaf load should be black. The color of leaf load should be black. Red property. For any red load, its child should be black. This is red load. Its child should be black. So a planner and its child should not be both red. Another property is called black property. For each load, all simple passes from the load to the descendant leaves contain same number of black loads. For example, for this load, if we go from 0 to the leaf to 1 leaf, then we must go through 2 black load, this black load and this low black load. If we go this load from another leaf, this pass also has two black load. This also has 2 black. This also has 2 black. This also has black. All paths has the same number of black loads. This is called black properties. The red-black tree. From the above properties, we can conclude that the height of red-black tree is at most this. For this red-black tree, if we that the height of this load is 1, then the height of its parent is 2. The height of this two load is 3. The number of elements n is equal to 6. And the height of the tree, the height of the tree is the height of the root is equal to 4, less than this. So for this tree, this property is okay. Now we prove this property. The height of red black tree is at most this number. To prove this property, we should talk about black height. What is black height? Black height is the number of black loads on any simple path from the load X to a leaf of the load, but not include this load. For example, for this load and this load, the simple path contain one black load. So the for this figure, we can see this load, the black height is 0, and for this load, the black height is 1, because from this path just one black load, from this path just one black load. So the black height is 1. This black height is also 1, because from these two to leave just one black load. For this load, the black height is 2, because there are 2 black load, except not to include this. We have a property. Any load X with height Hx has pH height, black height X larger than Hx divided 2. We can simply define red height equal to black height plus red height. But any path from a load X to leaf, the number of black loads larger than number of red loads. So this black height should be larger than this red height. So Hx less than 2 black height. And this is this property, black height larger than height divided 2. Red black tree has another property. A sub-tree loaded at any load X had at most this number of integral load. We can prove this property by induction. First, when pHx equal to 0, then at most this number integral. This is trivial. If pHx larger than 0, then the color of this child is red. If the color of the child is red, for this case, the pHx and ph child is same. Else, if the child of this node color, if the color of the child is black, then ph child equal to ph height, ph equal to phx plus 1. According to the inductive hypothesis, child for this case or this case must have at least this number of integral nodes. For the node x, the child have at least this number of integral node, and the right child also have this number of integral. So for this node, the integral number should be the integral number and the integral number of the right tree plus this node itself. So the integral nodes of x should be larger than this. This number is equal to this and equal to z. So we prove this property. With the two property, for any node x, at least this number of integral nodes. So n should be larger than this number. And we also have the property for the root of the tree, ph root should larger than h divided 2. H is height of the tree. Combine these two, we can have n larger than this plus 1, this larger than h divided r, so n larger than this, and this become this, and we can conclude h less than this. So we proved this property. So for red-black tree, if the number of elements is n, the height at most this. So the search, insert, delete operation will very efficiency because the height is at most this number. So the search time for BRT is OHO log 2n. Now we see how to insert a node in the red-black tree. If the tree is empty, insert node will be colored black, and to be the root, insert tree will be colored black and become the tree of the root. Else, if the tree is not empty, we use binary search tree insert operation to add the elements to the tree and color the node red first. Then we check if its parent is black. If parent is black, then okay, we did not destroy the properties of red-black tree. If parent is red, if this is inserted and the parent is red, then we will destroy the property. So we must do some adjustment. hold adjustment, we are using two operations. One is called recolor, and the other is rotation, just like the rotation in the AVL tree, to restore the BRT properties. For this case, we will do differently for two cases. One case is uncle is red, and the other case is uncle is black. Now we see how to insert a load from an empty tree. If the tree is empty, the inserter load will become the root of the RBT tree, and the color is black. We insert this number, and its parent is black, so okay, we return. We insert z number and the parent is black, so we do nothing. But if we insert this number, its parent is red. For this case, we must do adjustment. For this case, its uncle, the shear bin of its parent. The parent is 18. The shear bin of 18. This is the uncle of this load. The uncle is red. For this case, we will recolor the color of its parent and uncle from red to black. And we recolor its grandfather to red, except this load is root. If this load is not root, then we will make it red, and we repeat this process until we go to the root of the tree. But for this tree, this is the root of the tree, so we stop here. This is the first case. Another case, if we insert this load and its uncle is empty or black, its uncle is black or null. This is a null load, is also black. Null load is black. Its uncle is black. For this case, we should make suitable rotation and recolor. This rotation, we see this is LR type, so we will do two rotations. First, we rotate this to between them, and then we return this to between, become the right of. And we also recolor this load be black, because this load be black. And for its parent, if it is not the load, we will color it to red. But it is root of the tree, so we are done. We insert this number, and the uncle is red. So for this, we just recolor these two from red to black, and the grandfather from black to red. And for this kind, we will check its parent. If the parent is red, we will repeat the processing until become a red black tree. Okay, we can give the code like this. To insert a load, if the tree is empty, then this load is called back and becomes the root of the tree. We return. Otherwise, we give the inserted load color red, and while the parent of this load color, if the parent of this load color is red, we repeat the following processes. We check its anchor's color. If anchor's color is red, then we will make their color from red to black. If the ground parser is not ruled, then we make ground parser color to red, and X become the ground parser of X become X, and we go to the while. Else black, because the ground parser is root. We are done. This is a case, and another case, if the anchor's color is black, we should do a rotation LL, RR, LR, RL for these two cases and do some recolor. We can see this figure. Anchor X is the inserted load, and P is its parent, U is its anchor. They are red, so we color them to black, and the parent become red. But if this load is root, we will do not color the red. We just return. If the anchor is black, we will root according the four cases, one of the four cases, and recolor. For example, the anchor is black, and this is LL type. So we route these to here, come, and we do recolor. The ground parser become red, and its parent become black. For RR case, we do similar operation. Just rotate, left rotate. G becomes the left child of P, and its parent is colored black, from red to black, and the ground parser is colored red, color from black color to red. For LR case, we should first we need two rotation. First rotation X between the middle of the two loader, and do another rotation. G becomes the right child of X. And G is colored from black to red. X is from red color to black color. The last case, RL case, is similar. RL, we first rotation X between them, and do another rotation, left rotation G to become the left child of X, and X, the color of X from red to black, from red. The grandfather color from black to red. Okay, this is a red-black tree. I hope it is helpful. Thank you for watching my video.